Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast theater of cosmic catastrophes, few scenarios rival the devastation of a neutron star collision with Earth. To comprehend this apocalyptic event, we must first understand what neutron stars truly are, not just as astronomical objects, but as fundamental violations of our everyday physics. Born from the violent deaths of massive stars, neutron stars represent nature's ultimate compression experiment. When stars between 8 and 20 times the mass of our Sun exhaust their nuclear fuel, they undergo catastrophic core collapse. The outer layers explode outward in a supernova, while the core implodes with such violence that electrons and protons fuse into neutrons, creating matter so dense it defies imagination. Typical neutron star measures just 20 kilometers in diameter, roughly the size of a small city, yet contains more mass than our Sun. Picture this: a single teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. That's equivalent to the mass of Mount Everest, compressed into a volume no larger than a sugar cube. The surface gravity of these stellar remnants exceeds Earth's by a factor of 200 billion. A paperclip dropped onto a neutron star would hit the surface with the energy of a nuclear bomb. Their magnetic fields, typically a trillion times stronger than Earth's, would erase every credit card and hard drive from thousands of kilometers away and fatally disrupt the electrical signals in human bodies from similar distances. Most neutron stars rotate extremely rapidly, some completing several revolutions per second. These rotation rates, combined with their intense magnetic fields, generate powerful beams of radiation that sweep through space like cosmic lighthouses, what astronomers observe as pulsars. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. But how might one of these exotic objects find itself on a collision course with our home planet? While extraordinarily improbable, rogue neutron stars do exist. Most neutron stars remain gravitationally bound within binary systems or star clusters, but some receive powerful kicks during asymmetric supernova explosions. These kicks can accelerate neutron stars to speeds exceeding hundreds of kilometers per second, fast enough to escape their birth environments and become interstellar wanderers. Approximately 1 billion neutron stars populate our Milky Way galaxy alone. The vast majority orbit safely in the galactic plane, far from our solar system. The nearest known neutron star, RxJ 1856.5-37, lies about 400 light-years away, a comfortable buffer that has protected Earth throughout human existence. For our catastrophe scenario to unfold, we must imagine an exceedingly rare event: a rogue neutron star ejected from its original stellar neighborhood, entering our solar system on a trajectory that intersects Earth's orbit. The probability approaches zero, yet remains technically non-zero in an infinite universe, where even the most improbable events eventually occur, given sufficient time and space. As our hypothetical neutron star begins its approach toward the inner solar system, its effects would be detected years before impact. Gravitational disturbances would alter the orbits of trans-Neptunian objects, providing the first subtle warning signs. Later, intense radiation would become measurable by our space-based observatories, and eventually, its gravitational influence would begin to affect the orbits of our neighboring planets. Long before a neutron star would make physical contact with Earth, its approach would trigger a cascade of increasingly catastrophic effects. Our first detection would likely come from astronomers monitoring the outer solar system, who would notice inexplicable orbital perturbations among distant Kuiper belt objects. Computer models would eventually reveal a massive, compact object moving inward toward the Sun, a discovery that would immediately trigger worldwide scientific alerts. At a distance of 1 light-year, approximately 9.5 trillion kilometers, the neutron star's gravitational effects would still be minimal. However, its intense radiation would already be detectable by our most sensitive instruments. Radio telescopes would likely identify the object's pulsar emissions, rhythmic bursts of radio waves generated by its rotation, allowing astronomers to confirm the approaching object's identity as a neutron star. As the intruder crossed into the Oort cloud, the sphere of icy objects marking the outer boundary of our solar system, perturbations would become more pronounced. Thousands of dormant comets would be knocked from their stable orbits, many sent on new trajectories toward the inner solar system. This cosmic billiards game would unfold over months, creating spectacular but ominous meteor showers visible from Earth, the first visible harbinger of the catastrophe to come. When the neutron star reached the orbit of Neptune, approximately 4.5 billion kilometers from the Sun, its gravitational influence would significantly disturb the planet's motion. Similar effects would cascade inward as the massive object continued its approach, disrupting the orbits of Uranus, Saturn, and Jupiter. The destabilization of these gas giants would, in turn, alter the orbits of countless asteroids in the main asteroid belt, sending many toward the inner planets. At this stage, the neutron star would still be tens of astronomical units away, but Earth would already be experiencing serious consequences. Unusual tides would begin to appear in our oceans as the neutron star's gravitational pull competed with that of our moon. These tidal variations would start subtly, perhaps an extra few centimeters at first, but would increase dramatically. With each passing day, the approach would also trigger unprecedented seismic activity. Earth's crust, responding to the gradually intensifying gravitational gradient, would experience increasing strain. Fault lines worldwide would become more active, with earthquake frequency rising exponentially. Volcanoes long considered dormant would reawaken as magma chambers, previously held in delicate balance, responded to these new gravitational stresses. Earth's rotation would begin to slow as the neutron star's immense gravity exerted tidal braking forces on our planet. This deceleration would initially be imperceptible, measured only by atomic clocks, but would progressively intensify. Day length would increase by milliseconds, then seconds, disrupting everything from satellite orbits to biological systems evolved to precise 24-hour cycles. The most dramatic early effect, however, would come from radiation. Even from the distance of Mars's orbit, a typical neutron star's intense magnetic field would begin disrupting Earth's magnetosphere, our planet's natural shield against solar and cosmic radiation. The compression of our magnetic field would allow high-energy particles to penetrate deeper into the atmosphere, creating spectacular aurora displays visible even at equatorial latitudes. More concerning would be the effects on our technological infrastructure. Communications satellites would experience increasing interference. Power grids would suffer surges from induced currents. Global positioning systems would become unreliable. The resulting technological disruptions would complicate evacuation and emergency response efforts, even as governments worldwide struggled to develop contingency plans for a disaster with no historical precedent. Throughout this approach phase, Earth would remain physically intact, but human civilization would already be experiencing unprecedented stress as our planet's systems, geological, atmospheric, and technological, responded to the approaching stellar corpse. And these effects would only be the overture to the symphony of destruction to follow. As the neutron star closed to within the orbit of Mars, approximately 225 million kilometers from Earth, its gravitational effects would escalate from disruptive to catastrophic. Tidal forces would become the primary agent of destruction long before any physical contact with our planet. The fundamental physics of the situation are straightforward but merciless. Gravity decreases with the square of distance, meaning that the side of Earth facing the neutron star would experience substantially stronger gravitational pull than the far side. This differential force would create a tidal bulge far more extreme than anything produced by our moon. At a distance of 10 million kilometers, about 25 times the Earth-Moon separation, ocean tides would reach hundreds of meters high. These would not be gentle, rhythmic tides, but rapidly intensifying walls of water that would advance kilometers inland, obliterating coastal infrastructure worldwide. Evacuation from coastal regions would become impossible as transportation. Networks collapsed under the twin pressures of physical damage and mass panic. More devastating still would be the solid body tides. Earth's crust would begin to deform visibly, rising and falling by tens of meters over cycles of hours, as our planet rotated relative to the approaching neutron star. This flexing would shatter tectonic plates, triggering simultaneous mega-earthquakes across all fault lines. The seismic activity would far exceed magnitude 10 on the Richter scale. Beyond anything in recorded history, the crustal deformation would rupture magma chambers globally. Hundreds of volcanoes would erupt simultaneously, including many previously considered extinct. The supervolcano at Yellowstone, dormant for 640,000 years, would awaken catastrophically. Similar structures at Lake Toba in Indonesia, the Phlegraean fields in Italy, and other sites would follow. The resulting ash clouds would circle the globe, blocking sunlight and creating an instant volcanic winter, though this atmospheric effect would soon be rendered irrelevant by even greater destruction. Earth's rotation would be drastically affected, first slowing and then potentially stopping altogether, as the neutron star's tidal forces locked our planet in much the same way Earth has tidally locked the Moon. This rotational disruption would generate tremendous frictional heating in Earth's interior and further intensify both seismic and volcanic activity. The magnetosphere, already compromised during the approach phase, would collapse entirely under the overwhelming influence of the neutron star's magnetic field. Unfiltered cosmic radiation would bathe the planet's surface, delivering lethal doses to any exposed organisms within minutes. Electronic systems worldwide would fail simultaneously, eliminating any remaining technological means of monitoring or responding to the unfolding catastrophe. As the distance closed to 1 million kilometers, about 3 times the Earth-Moon separation, the neutron star's gravity would begin to overcome Earth's structural integrity. Tidal forces would stretch our planet along the Earth-neutron star axis, distorting our once spherical world into an increasingly elongated ellipsoid. This deformation would grow more extreme with each passing hour, until the forces exceeded the tensile strength of rock itself. At this point, approximately 3 to 4 hours before actual collision, Earth would begin to fragment. The side nearest the neutron star would experience accelerations exceeding Earth's own gravitational binding, causing continental fragments to detach and begin falling toward the approaching stellar corpse. The planet's core would remain temporarily intact due to its greater density and strength, but the crust and mantle would disintegrate into a stream of rocky debris. Earth's atmosphere and oceans would boil away from the combined effects of tidal heating, volcanic outgassing, and direct radiation. Any humans who somehow survived the earthquakes, volcanic eruptions, and radiation would witness the sky literally being torn away as atmospheric gases were stripped from the planet and pulled toward the approaching neutron star. By the time the neutron star closed to within 100,000 kilometers, Earth as a coherent planetary body would cease to exist. What remained would be a rapidly elongating stream of increasingly fragmented rock, metal, and vapor, the funeral procession of our once habitable world. The actual collision between Earth's remains and the neutron star would occur in stages, as the gravitational disintegration would have already transformed our planet into a stream of debris. This debris would not strike the neutron star simultaneously, but would instead form an accretion disk before the final plunge. The physics governing this collision operate in realms far beyond everyday experience. The neutron star's escape velocity, the speed needed to break free from its gravitational pull, exceeds half the speed of light. This means Earth's fragments would accelerate to velocities of tens of thousands of kilometers per second during their final approach. At these velocities, matter doesn't behave as it does under normal conditions. The kinetic energy of impact would be so extreme that atomic and molecular bonds would break instantly. The first particles of Earth to reach the neutron star's surface would strike with energies millions of times greater than those produced in the most powerful particle accelerators humans have built. The temperature at the impact sites would soar to billions of degrees Kelvin, hotter than the cores of most stars. Under such conditions, matter exists as plasma, a soup of dissociated atomic nuclei and electrons. The incoming debris would be compressed by the neutron star's gravity to densities approaching nuclear matter, approximately 400 trillion kilograms per cubic meter. This compression would trigger nuclear fusion in the lightest elements from Earth's debris. Hydrogen atoms would fuse into helium, releasing enormous energy. Heavier elements would undergo rapid neutron capture, creating increasingly massive nuclei in sequences impossible under normal stellar conditions. Some of these reactions would momentarily create super-heavy elements never observed in nature, before these exotic nuclei disintegrated from instability. The neutron star's magnetic field would interact violently with the incoming charged particles, accelerating them to relativistic speeds and generating intense electromagnetic radiation across the spectrum. The streams of charged particles spiraling along magnetic field lines would produce synchrotron radiation, primarily in X-ray and gamma-ray wavelengths, creating brilliant emission visible across much of the galaxy. As more material accumulated, on the neutron star's surface, localized thermonuclear explosions would occur. Unlike the controlled fusion in stellar cores, these would be chaotic explosive events. The neutron star's surface would briefly exhibit luminosity hundreds of thousands of times greater than our Sun, despite its small size. The angular momentum of Earth's fragments would not disappear, but would be transferred to the neutron star. This influx of rotational energy would potentially increase the neutron star's spin rate. If the rotation became rapid enough, approaching 1,000 revolutions per second, the neutron star might emit gravitational waves detectable by sensitive observatories throughout our galaxy. The collision would also disrupt the delicate balance of forces within the neutron star itself. Neutron stars exist in a state of equilibrium between the inward pull of gravity and the outward pressure of neutron degeneracy, the quantum mechanical resistance of neutrons to further compression. The sudden addition of Earth's mass, though small compared to the neutron star, less than 1/1,000,000th of its total, could potentially trigger oscillations in the neutron star's structure. These oscillations, known as starquakes, would momentarily crack the neutron star's crystalline crust, releasing enormous bursts of energy. A typical neutron star starquake can release energy equivalent to a magnitude 23 earthquake, billions of times more powerful than anything possible on Earth. The influx of new material might trigger multiple such events in rapid succession. Throughout this catastrophic process, the laws of physics would remain unchanged, but they would operate at extremes far beyond human experience. The energies, densities, magnetic fields, and gravitational forces involved would momentarily create conditions that existed only during the earliest moments after the Big Bang or in the cores of exploding supernovae. From a safe distance of several light-years, the collision would appear as an intense flash of high-energy radiation, followed by a prolonged glow as the neutron star's surface cooled from its brief but spectacular heating. This emission would be detectable across much of the Milky Way galaxy, a cosmic tombstone marking the location of humanity's former home. In the hours and days following Earth's obliteration, the neutron star would begin to stabilize into a new equilibrium state. The immense energy released during the collision, approximately 10 to the 38 joules, equivalent to Earth's entire gravitational binding energy, would gradually dissipate into space as electromagnetic radiation and neutrinos. Most of Earth's mass, approximately 5.97 times 10 to the 24th kilograms, would become incorporated into the neutron star. Given that a typical neutron star contains about 2.8 times 10 to the 30 kilograms of matter, Earth's contribution would increase the neutron star's mass by only about 1 part in 5 million, a minute addition from the cosmic perspective, yet representing the complete physical legacy of our planet. This additional mass would be primarily distributed across the neutron star's surface, rather than penetrating deeply into its interior. The neutron star's crust, a crystalline lattice of neutron-rich nuclei approximately 1 kilometer thick, would absorb much of Earth's matter. The heavier elements from Earth's core, primarily iron and nickel, would settle deeper into this structure, while lighter elements would remain closer to the surface. The neutron star's incredibly strong gravity would compress Earth's elements to extraordinary densities, forcing electrons to combine with protons and form additional neutrons. This process, called neutronization, would transform much of Earth's familiar matter into exotic neutron-rich material, unlike anything that existed on our planet. Over time, these new neutrons would migrate inward, becoming indistinguishable from the neutron star's original composition. One of the most visible short-term changes would be to the neutron star's magnetic field. The influx of charged particles would generate complex disturbances in the magnetosphere, potentially altering the orientation of the magnetic poles or creating localized magnetic anomalies. For any pulsar emissions the neutron star previously generated, this could manifest as temporary irregularities in pulse timing and strength, signals that distant alien astronomers might detect and recognize as evidence of a recent planetary collision. The neutron star's rotation would be affected in complex ways. While the total angular momentum of the Earth neutron star system would be conserved, the distribution of this momentum would change. Depending on the precise angle of impact and distribution of Earth's fragments, the neutron star might experience either a slight increase or decrease in its rotation rate. These rotational effects, though small, would be measurable through changes in pulsar timing. More dramatically, the collision would likely trigger substantial starquakes, sudden adjustments in the neutron star's crust. These events would release enormous bursts of energy, primarily as gamma rays and X-rays. A series of these starquakes might continue for years or even decades as the neutron star's structure gradually settled into its new configuration. The material not immediately incorporated into the neutron star, perhaps 1 to 5% of Earth's mass, would form a temporary accretion disk. This disk would contain a mixture of vaporized rock, metal, and the remains of Earth's hydrosphere and atmosphere. Subjected to intense radiation and tidal forces, this disk would gradually spiral inward toward the neutron star's surface. As this material accreted, it would be compressed and heated to temperatures of millions of degrees, causing it to emit thermal radiation primarily in the X-ray spectrum. This accretion process might continue for months or years, until virtually all of Earth's material had been consumed or ejected from the system. A small fraction of the most energetic particles might actually achieve escape velocity and be ejected from the system entirely, carrying with them trace elements that once formed part of Earth. These particles, accelerated to near light speed by the neutron star's magnetic field, would join the cosmic rays that permeate our galaxy, perhaps the only component of Earth destined to journey beyond the neutron star's gravitational prison. From these violent processes would emerge a neutron star essentially unchanged in its fundamental nature, yet bearing subtle signatures of its encounter with our world. Earth would not leave a visible scar, but rather a ghost, encoded in slight alterations to the neutron star's mass, composition, rotation, and magnetic field. While Earth would be the primary victim of the neutron star collision, the entire solar system would undergo profound transformation. The Sun and remaining planets would continue to exist, but in a configuration permanently altered by the catastrophic encounter. The Sun, with its mass of approximately 2 × 10⁻30 kilograms, over 300,000 times Earth's mass, would remain gravitationally dominant in the system. However, the neutron star's passage would dramatically disrupt the delicate gravitational balance that has maintained planetary orbits for billions of years. As the neutron star departed, assuming it wouldn't be captured by the Sun's gravity, it would carry away kinetic energy and angular momentum from the solar system. The Sun would experience a small but measurable gravitational recoil, slightly altering its position and velocity relative to the galactic center. This perturbation would be sufficient to disrupt the Sun's orbit within the local interstellar cloud, potentially altering its long-term trajectory through the Milky Way. More immediately apparent would be the effects on the surviving planets. Mercury and Venus, being interior to Earth's orbit, might experience less severe gravitational disruption depending on their positions during the neutron star's passage. However, both would still undergo significant orbital changes, possibly being ejected from the solar system entirely or thrown into new, highly eccentric orbits that might eventually intersect with the Sun. Mars, the next planet outward, would likely experience even more dramatic orbital changes due to its proximity to Earth. In some scenarios, the red planet might be captured by the passing neutron star and torn apart in a process similar to Earth's destruction, though more prolonged due to its more distant initial position. The gas giants, Jupiter, Saturn, Uranus and Neptune, would experience less immediate destruction due to their greater distances and masses, but their orbits would be irreversibly altered. Jupiter, with its substantial mass and resulting gravitational influence, would play a crucial role in the solar system's post-catastrophe evolution. Its altered orbit would, in turn, affect the trajectories of countless smaller bodies throughout the system. The asteroid belt would be thoroughly disrupted, sending thousands of large bodies and millions of smaller fragments into new, often unstable orbits. Many of these would eventually impact the surviving planets or the Sun, while others would be ejected into interstellar space. Similar disruption would occur in the Kuiper belt beyond Neptune, destabilizing dwarf planets like Pluto and sending cometary bodies inward toward the Sun. The most extensive transformation would occur in Earth's former orbital vicinity. The Moon, having been ripped away from Earth during the planet's disintegration, would likely not survive intact. Depending on its position during the catastrophe, it might be captured by the neutron star alongside Earth's remains, torn apart by tidal forces, or left in a highly eccentric solar orbit as a lonely monument to its former host planet. In the space once occupied by Earth's orbit, a sparse ring of debris might temporarily form. This material, consisting of fragments that escaped both Earth's disintegration and the neutron star's gravity, would range from dust-sized particles to possibly a few larger fragments ejected early in the encounter. Over decades, this material would disperse due to the combined gravitational influences of the Sun, surviving planets and radiation pressure. Perhaps most significantly, the delicate resonances between planetary orbits, gravitational relationships that have helped stabilize the solar system over billions of years, would be permanently disrupted. The clockwork precision of our current planetary configuration would give way to chaotic evolution, with orbits becoming increasingly unpredictable over astronomical timescales. From a cosmic perspective, the solar system would be transformed from an unusually stable, life-supporting stellar system into a gravitationally traumatized arrangement bearing the unmistakable signatures of catastrophic disruption. Alien astronomers studying our system in the distant future might find it notable primarily as evidence of a rare stellar collision rather than as the former cradle of a technological civilization. The total time frame for these system-wide changes would vary dramatically by distance. While Earth's destruction would unfold over hours, the complete gravitational reorganization of the outer solar system would require centuries or millennia to fully manifest. The final configuration might not stabilize for millions of years, a cosmic restructuring triggered by a single catastrophic encounter with an interstellar intruder. In contemplating this apocalyptic scenario, we naturally wonder, could humanity detect such a threat in time to respond, and what responses might be possible? The answers reveal both the remarkable capabilities of modern astronomy and the fundamental limitations of our technological civilization. Detection capabilities represent our first critical defense. Current astronomical survey programs focus primarily on near-Earth objects, asteroids and comets that might impact our planet. These systems are designed to detect relatively small, nearby objects rather than massive distant ones. However, all-sky surveys like the Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, will continuously map the entire visible sky, potentially capable of identifying distant neutron stars moving against the stellar background. A neutron star approaching our solar system would eventually become detectable through multiple means. Its gravitational influence would disturb the orbits of trans-Neptunian objects and outer planets long before reaching Earth. These perturbations would be subtle but measurable by precise astrometric observations. Additionally, most neutron stars emit distinctive radiation, particularly as pulsars, that our radio telescopes could detect at distances of several light-years. Realistically, we might identify such an approaching object decades before impact, sufficient Time to confirm the threat, but presenting monumental challenges for response. The fundamental physics of the situation creates a sobering reality. Once a neutron star was confirmed on collision course with Earth, humanity would face an extinction-level threat beyond our capacity to prevent. No existing or foreseeable technology could alter the trajectory of an object with a neutron star's mass. The energy required would exceed humanity's total energy production by countless orders of magnitude. Nuclear weapons, our most powerful technology, would have no measurable effect on the neutron star's path. The gravitational binding energy of a neutron star exceeds Earth's entire energy output throughout human history by a factor of roughly 10 to the 24th power. Faced with inevitable planetary destruction, humanity's only possible response would be attempted evacuation, not of our planet's population, but of its knowledge, cultural heritage, and potentially a small representative sample of its life forms. The decades of warning might allow for the construction of automated arc vessels carrying digital libraries, DNA samples, and possibly human embryos in suspended animation. These arcs would need to be launched well before the neutron star's approach, destabilized Earth's environment. Their destinations would necessarily be beyond our solar system, as even the outer planets would eventually experience severe disruption. The technology for such interstellar missions currently exists only in preliminary form, requiring substantial advancement to become viable in the time frame available. More realistically, humanity might prioritize establishing self-sustaining colonies on Mars or potentially habitable moons of the outer planets before Earth's destruction. While these colonies would face severe challenges after the neutron star's passage disrupted the solar system, they might offer humanity's best chance for short to medium-term survival. Communication with other potential civilizations might become a priority. Advanced radio broadcasts carrying the sum of human knowledge, directed toward nearby star systems with potentially habitable planets, could preserve humanity's intellectual and cultural legacy even if our species did not physically survive. The neutron star collision scenario illustrates the ultimate vulnerability all planetary civilizations face. We exist at the mercy of cosmic forces vastly more powerful than our technological capabilities. Yet this vulnerability need not render our existence meaningless or our efforts futile. The statistical improbability of such a collision, measured in timescales far exceeding Earth's remaining habitable lifetime, provides practical security against this specific threat. More importantly, understanding such existential risks motivates expansion beyond our single planetary home. The development of self-sustaining colonies throughout and eventually beyond our solar system represents humanity's ultimate insurance policy against extinction. Whether from neutron star collisions or any other cosmic catastrophe, the universe operates without malice, but also without mercy. Its physical laws create both the conditions for our existence and the potential mechanisms for our destruction. By understanding these laws and expanding our presence beyond a single vulnerable world, humanity might eventually achieve a level of dispersion and resilience that no single catastrophe, however violent, could entirely eradicate. In this way, the contemplation of even the most extreme cosmic disasters serves not to paralyze us with fear, but to inspire the expansion, diversification, and ultimate preservation of Earth's remarkable evolutionary experiment, a species capable of understanding the very forces that threaten its existence.